All right, we're going to do one more example for concavity. I do notice I have my numbering incorrect in the notes, so would you please change this to number 4? All right, so this time there's a slight change. We're going to discuss domain, but we're adding in increasing and decreasing regions as well as concavity and inflection points. So sort of putting it all together. So let's begin with first, let's talk about the domain of this function g. And notice that it has part of it is the logarithm function. And we know the logarithm is defined for the argument being greater than 0. The linear part has no domain restrictions, but the log does. So the domain of g is the x's have to be greater than 0. Okay. So that takes care of domain. All right, now to talk about increasing and decreasing, you have to recall that that's the first derivative that we're looking at. So this is looking at when the first derivative is greater than 0, and we're looking at when the first derivative is less than 0 for decreasing regions. Okay, so let's test that out. All right, first derivative. All right, so this g prime of x. Well, the derivative of ln of x is 1 over x minus, and the derivative of x is 1. All right, so I need to know where this is increasing and decreasing. So just like with the concavity, remember that we're going to look for where g prime is equal to 0 and when it's undefined. So right away, I can see that we have an x in the denominator. So that would mean we have an undefined value at x equals 0. So I'm going to write that down. G prime undefined at x equals 0. Now I'm going to see if there are any other, so do we have a place where the derivative equals 0? So I take this derivative and I set it equal to 0. So 1 over x minus 1 equals 0. Let me add 1 to the other side. So that gives me 1 equals 1 over x. And then if I cross multiply, whatever, the only solution to this is when x is equal to 1. And so we can see that if we have 1 here, that's 1 over 1 minus 1, that would be 0. So g prime equals 0 at x equals 1. So I have my two values that I'm going to do a number line test for. So it's just like the second derivative. Okay, and so I'm going to put those numbers, so 0 and 1, go on the number line. And then I'm going to look at g prime around those numbers. So let's choose, how about in the left interval, we'll choose x equals -1. In between, how about x equals 1/2? And to the right of 1, x equals 2. So we're going to test those three numbers at g prime. So g prime of -1. All right, so goes into here. So 1 over -1, that's -1, 1 over -1, and then -1. All right, well, that produces a negative number. So it's g prime is negative in the first region, first interval, and 1/2. All right, g prime at 1/2. All right, so that's going to be 1 over 1/2, and then -1, which is essentially, that's a complex, that's 2 minus 1, well, that's greater than 0. So positive here, and then g prime at x equals 2. So we're testing the right region, right interval. So that would give me 1 over 2. 1 over 2 minus 1, which is a negative number. So we went back to g prime being negative. And so now I need to state my conclusions about this. So that means that G. So where the regions where G prime is negative, that means that the original function is decreasing. So so G is decreasing in the first and the third region, and then it's positive. G prime is positive here, so G is increasing. All right, so let's write that. G of x is increasing on the interval from 0 to 1 because G prime is greater than 0. All right, G of x is decreasing on the interval. Oh, well, there's actually two intervals. So from negative infinity to negative 1. And then the second interval is from 1 to infinity because G prime is less than 0. All right, so this is my second conclusion that I've made. So increasing, decreasing, I figured that out. Now I'm going to talk about concavity. All right, so now we need the second derivative. So let me write that again. So what do I have for G prime of x? All right, G prime is this. I'm going to write that as a power. So that's x to the minus 1 over x minus 1. All right, now I use the power rule. So G double prime of x is equal to negative 1x to the negative 2, and then the derivative of the constant is 0. So there is my derivative, which works out to negative 1 over x squared. Again, I need to know where the second derivative is equal to 0. Since the numerator is never 0, there are no zeros for the second derivative. Where is it undefined? Well, the denominator could be 0 and at x equals 0. So G double prime is undefined at x equals 0. Okay, so that will be the only value I will use to break up the intervals. And so now I'm going to draw a number line. And place 0 on it. And I'm going to evaluate G double prime at values around that. And so how about we test negative 1 and positive 1. All right, so G double prime at negative 1 would be, all right, so negative 1 in here. So that's negative 1 in the numerator, so that's negative 1. And then we're squaring my input. So negative 1 squared would be positive 1. And that ratio is negative. And now I test G double prime at 1. And so that would again be negative 1 in the numerator over 1 squared, which is 1. And so this is negative again. So in both of these regions, it's negative. And and it kind of makes sense. If you take a look at the second derivative, the numerator is always negative and the denominator is always positive. So no matter what you do, you're always going to get a negative divided by a positive. And so this will always be less than 0 for every x, except of course, at x equals 0, which for which the second derivative is undefined. And notice, well, I kind of left something off. If I forgot something, and I'm glad I wrote it in the beginning, because now I'm looking back and going, wait a minute, whoa, Nelly, right? There's this domain. It says the domain of G is greater than 0. So I shouldn't even be testing these values over here. So I'm going to get my red pen out. Whoops, wrong thing. Go back, get my red pen out. And we're going to just eliminate this interval. We can't test this side of 0 because it's not in the domain. So we did extra work for no reason. So we have to stick to values greater than 0. 0 isn't even in the domain. So even though that created a breakpoint for us, we only can test values to the right. So this function is concave down for all values to the right of 0. It's always concave down. So G is concave down on the entire domain, which for x greater than 0, since, oops, I don't spell, uh-oh, I don't know what I just hit. I have no idea. Okay. Okay. Since G double prime is less than 0 on the entire domain. It's always concave down. And so that's the conclusion for my concavity. Of course, there are no inflection points. We have no change in concavity and no defined points for the T that we even tested. So there's no inflection points. So let me write that. In case it's asked, if it's asked, what are the inflection points, then you need to answer it. There are no inflection points. You have to state it. You can't just ignore it if there aren't any. So I'm going to write it down so I can get my point for my AP test. All right, so have I answered everything? Let's see, I talked about concavity, I talked about inflection. I've got everything checked off, and there are all my answers for each part, including domain. And that concludes my final example. All right, good luck with your